want to give a brief overview why I believe that data science is absolutely key to Uber and its future. This is really a combination of different factors that come here together. We are making decisions in real time at global scale, whilst needing to take into account the local nuances of the marketplaces. And of course, we also want to incorporate the user preferences on the product. Now, unsurprisingly, Uber has heavily invested in data science from early stages on. And these days, we have hundreds of data scientists working across the company to solve this complex problem. So as a result of this, we are constantly seeking to increase the innovation speed with which these data scientists move. And so today, I'm going to talk about how can we get to more accurate as well as higher innovation speeds using platforms and tools. We started off this journey by building platforms and tools by our data team that are integrated both externally as well as developed in-house in order to increase the innovation speed for data scientists and analysts. But we didn't stop there. We then started to hire domain experts in various different fields, such as forecasting, anomaly detection, conversational AI, and computer vision, just to name a few. And together with their cross-functional counterparts in engineering, product, and design, these teams build platforms and tools that can transform anyone at Uber into a data scientist, with the grand vision of making this possible just at a push of a button, of course with best practices and guardrails incorporated. So let's look at the 4 major lifecycle stages of a typical data science project that we aim to accelerate. In the first step, there is data exploration, followed by iterative prototyping. Once a good model is found, it gets productionized, and of course, during the rollout process and post-rollout process, we want to actively monitor performance of the model. This closes the first generation of model development stage, and it can start anew if necessary. Now, at the beginning of any such endeavor stands, of course, the data and building a data science team. And so I first want to share some early stage insights that we've gathered from this process. Let's start with data, because without data, there is no science. The way I think about data is like growing a garden. It needs constant attention and grooming. This is particularly important because otherwise, data scientists need to over and over again deal with data fundamentals, potentially poor quality of data, discoverability issues, and many other things. So really investing early in a solid data foundation can have great effects that are compounding in returns. Next comes the exploration stage. Here, my strong suggestion is that data scientists also perform the product analytics. This really has a lot of advantages, even if they're data analysts on the team. The first one is that the data scientists stay close to the business and the product and the user experience. And this really translates into the model choices that are being made. Secondly, it also elevates the data analysts to equal partners to data scientists, which is really important to me and is also critical for team health. Next comes the iterative development stage. Here we have found it to be extremely important to have data science best practices. Now, this is of course important at any stage of the life cycle, but stands out in particular in this iterative prototyping stage. As obviously we're a very nascent job family, there are no standardized processes and best practices yet in place across the industry. And so we have heavily invested in order to define such best practices that are heavily leaning on engineering best practices, whether it is checking in code and getting it reviewed by data scientists as well as engineers, having technical documentation that is reviewed by peers, and many other things. This allows for high quality assurance as well as reproducibility. When it comes to productionization, we heavily invest in so-called full-stack data scientists. These are data scientists that also can write production-level code. We see a lot of advantages on this front. From a developer velocity standpoint, it allows us to move immediately from finding a good prototype into production. We are not being delayed by freeing up engineering resources, which at the time might be working on other things, and could delay the productionization by weeks or potentially months. process. It also helps us to identify viable algorithms early in the design phase, because what might look good on paper might not work well in practice at scale under various different constraints of the corresponding architectures. And finally, we minimize any handoff errors that might be happening as a result. Now, finally, with monitoring, this is a task that both developers as well as data scientists really don't like to participate in. And so here the philosophy is making the right path the easiest path, and ideally automating as much as possible. And we'll be briefly touching on this topic later on. So now let's look at some of the platforms and tools that our data team have developed in order to accelerate every single step of this four-stage life cycle that I just showed you. The first one is around data exploration. And as we talked about, investing heavily in data quality, maintenance, metadata, and various different other things is extremely critical. So to this end, our data team has built a platform that allows for surfacing and maintaining metadata at scale, allowing us to quickly transform data into knowledge. On the right-hand side, you can see Kepler.gl. This is a web-based, data-agnostic, highly performant application that allows for visualization of large spatiotemporal data sets. As you can imagine, at Uber, we have a wealth of problems in the spatiotemporal domain. Kepler.gl has been open-sourced approximately a year ago and has found a lot of attraction externally, with over 75,000 Uber external users and over 5,500 GitHub stars. Moving on to the development phase, the data team has here developed what is known as Data Science Workbench. It is an IPython Notebook++ that is deeply integrated into our data stack, allows for version control and sharing. It has also recently been heavily integrated with our machine learning platform, Michelangelo, to allow for easy deployment of machine learning models. On the right-hand side, you can see Horvath. This is Uber's open source distributed deep learning framework for TensorFlow, which has broken new ground in training speeds for deep learning models. Now, when it comes to productionization, Uber has heavily invested in an in-house machine learning platform called Michelangelo. It allows us to leverage off-the-shelf models at scale, including deep learning models. In addition to this, they have recently allowed data scientists to bring their own Python code using PyML and to run it in a sandbox environment. When it comes to monitoring, we have both a real-time anomaly detection platform I'm going to talk about a little bit later, as well as an experimentation platform that allows for rollout monitoring and experiment setup at scale. And of course, these tools have empowered us, data scientists and analysts, tremendously throughout our journey and have helped us increase the innovation cycle tremendously. But we didn't want to stop there. We wanted to transform anyone within the company into a data scientist. And this is where the platform teams come into play. They are domain experts in various different fields, such as forecasting, anomaly detection, conversational AI, computer vision, and experimentation. And these data science ninjas, as I like to call them, work cross-functionally with their counterparts in product, engineering, and design to build platforms and tools that others can utilize across the company, making these expertise available at a push of a button, of course with guardrails and best practices incorporated. We have been working towards commoditizing various different fields of data science for the last few years, including forecasting, anomaly detection, experimentation, and more recently also conversational AI and even data analytics. And so today I'll be touching on three major initiatives that help with commoditization of data science at Uber. The first one being our forecasting platform. Here the grand vision is to provide highly accurate, cutting-edge forecasts at a touch of a button without any forecasting expertise required from the end user. The only input required by the end user is historical data, for example, in the form of a CSV file or in the form of a query, as well as the forecast horizon, as in how far the user wants to forecast out. We then do everything automatically in the background, and I'll be showing you how we'll be doing it in the next few slides. The output then, as you can see here on the graph, is this blue line, as well as the yellow and red prediction intervals that give a sense of uncertainty, which allows our stakeholders to make actionable business decisions. Some of the things that we're looking at before we platformize is, are there sufficient number of use cases across the company that warrant the large investment of platformization? Other factors include whether each of these use cases has a step function improvement to our user experience, and whether the modules that we build out are transferable and reusable across the various different use cases. And for each of the three platforms I'm going to show you today, the answer is yes. Now, looking at the forecasting space, there is a plethora of use cases across the company. Here I'm just showing three select ones. The first one being marketplace forecasting, which forecasts in spatiotemporal fine granular fashion both supply as well as demand across our marketplaces. In the middle column, you can see our systems outage detection. We want to detect in real time whenever the app is not functioning as expected, such as that people cannot sign in, sign up, or potentially cannot take a trip. Now, this is a very challenging problem because many of our data look like, as you can see here in the time series, and have day and night cycles, rapid underlying growth, as well as some variability on minute-by-minute basis. We have a very large number of these time series, over 500 million, and of course we want to detect it as quickly as possible. Now, we also want to have the signal-to-noise ratio be very high because we're potentially waking up people in the middle of the night who are on call, and nobody wants to be woken up just to find out that there's a Justin Bieber concert just finishing. So we have to be highly accurate in our forecasts. And as you can see here in the middle, we have found a way to dynamically calculate and update such prediction intervals that we use in order to understand whether a system anomaly might be happening or not. This is completely automated. The only thing that the end user needs to provide us with is a list of business critical metrics. Everything is done completely automatically besides that. The final example and use case I want to present to you today is hardware capacity planning. At Uber, we still have a lot of hardware on-premise. And so we obviously want to be fiscally responsible and not provision too much hardware, whilst at the same time not under-provision, which could yield outages and lose the trust of our end users. So we really want to apply the Goldilocks principle, not too much and not too little hardware. Forecasting this hardware can be quite challenging, especially for special event days that are of high demand, such as Halloween and New Year's Eve. And our teams have found proprietary algorithms that can do that highly accurately. Now let's look at some of the typical forecasting stages of a forecasting project. The first one is data exploration and pre-processing. Now pre-processing is often an overlooked step in the forecasting lifecycle and can be as important, if not more important, than finding the right architecture of, for example, a deep learning model. To this end, we have built modules that automatically can detect and handle pre-processing steps that are typically found in both statistical as well as machine learning approaches. The next step is to find the right forecasting methodology. There are three major categories. On the left-hand side, you can see the classical statistical approaches, such as your typical ARIMA or Holt-Winters. I've also included the theta method here, which is a less well-known methodology, but we found to be extremely useful because it is computationally very cheap, it works well on our time series, and it has won the famous international M3 forecasting competition. Now, in more recent years, also machine learning has entered the forecaster's toolkit, and methodologies such as quantile regression forests, as well as deep learning methodologies, especially recurrent neural networks and long short-term memory approaches have become very popular. The third category is a hybrid approach between these two, combining both classical statistical approaches, as well as deep learning methodologies. One of our team members, Slavik Srul, has developed such a novel hybrid approach and has won the famous international forecasting competition M4 with this approach. Now, the bottom line is that one really can't forecast which of these methods will work best on a given use case, and so one has to try out several different forecasting approaches. In order to scale this, we have developed a parallel language-extensible backtesting framework that can scan through a multitude of different forecasting algorithms. Here we have integrated two major backtesting approaches. On the left-hand side, you can see the so-called sliding window approach, where you have a constant window size of both training as well as testing, and through the passes, more historic data gets dropped. On the right-hand side, the expanding window approach. As the name suggests, here the training window size increases time step over time step, whilst the testing window stays constant. This is particularly useful if your time series are short. Now we can combine this backtesting framework with a whole suite of forecasting algorithms that we have integrated off the shelf or developed proprietary in-house. And of course, for any power users, we also provide statistics around the performance of these algorithms, as I'm showing for illustrative purposes here in this two-dimensional diagram. So now this concludes the most basic fundamental steps of a forecasting problem that we're able to semi-automate and fully automate. I would like to now move on to some more of enhanced capabilities of our forecasting stack. As you saw in the hardware capacity planning example, special events such as holidays, as well as sporting, weather events can have large impact on our business metrics. And so, of course, any forecasting methodology should be incorporating an estimate of the impact of such events. The classical statistical approaches don't fare well with external factors. Either they cannot incorporate them at all, or they do not perform well if they do. To this end, we've been heavily investing in both machine learning and deep learning approaches. And here on the slide, you can see one of the architectures that we have implemented. Keeping in mind the velocity component and automation component that we're trying to accomplish, I would like to point out in the pre-training step that we're applying an encoder-decoder approach in order to automatically extract features from the time series. This learned embedding is then concatenated with various different external events, such as holidays, weather, and sporting events, and then multi-layer perceptron is applied in order to get the final forecast. In case you're interested in more details, we have also published a white paper on this topic. We also have heavily invested in deeply integrating this forecasting stack into our data. This allows us to provide forecasts programmatically at scale. We also are heavily invested in quality assurance, both in terms of the data that is flowing into our platform, as well as assuring high quality for the forecasts that we're providing to our end users internally. The next example of commoditization of data science I want to talk about is natural language and conversational AI. And in order to illustrate some of the core components of a problem in this space, I would like to touch on one-click chat, which is a recent product that we have launched, which facilitates the communication between riders and driver partners during the pickup experience. As you can see in the example provided on the slide, instead of the user having to type in a response to an incoming message, we now have a machine learning algorithm that understands the incoming message and makes smart response suggestions to the end user, and they just have to tap merely on one of these suggestions in order to reply. Now, framing this from a natural language perspective, there are two major steps involved here. The first one is when a writer, for example, sends an incoming message, then the algorithm algorithm understands the topic of conversation, also known as the intent. This is a recurring theme when it comes to natural language and conversational AI use cases. Now, once the topic of conversation or intent is known, we can look up predetermined responses based on each of these topics and surface them to the end user, in this case, for example, a driver partner. Now, this all sounds very straightforward, but in practice, there are quite a few challenges with this particular use case. The reason for this is that the messages are very short, there are often abbreviations, misspellings, and also autocorrect is not our friend. As you can see from this real-world example that I've incorporated at the bottom of the slide, I'm Washington for you should clearly mean I'm waiting for you. So any algorithm that we choose needs to really incorporate the semantic meaning of the underlying sentences. As you can see from additional examples on this slide, you might get examples where different words have very similar meaning, and in other examples, different words have very different meanings. So again, the algorithm needs to be able to tackle all of these things, and a typical frequency-based approach would not be able to handle this very well. As a result, we have used Doc2Vec, which was developed by Google, in order to capture this semantic understanding. We have trained it on anonymized Uber data, and it was very interesting for us to see that the I'm Washington you, for example, was correctly understood as I'm waiting for you after we were done with our process. Again, I want to capture some of the many natural language use cases that we have at Uber in order to ensure that when we're platformizing, that things can be both transferable as well as applicable across a wide range of different use cases. In addition to the one-click chat example that I just covered, we are also working on hands-free dispatch currently, which will allow driver partners to respond to the incoming dispatch system with a yes or no answer. Secondly, voice reply, which will be in addition to the one-click chat feature. Now the driver partner can again respond in voice to an incoming rider message. On the far right-hand side, you can see an initiative that is called Customer Obsession Ticket Assistant, which we have been building in our customer care initiatives. Here we built an AI that empowers our customer service representatives. It understands the incoming text from a customer support ticket and then makes suggestions to the customer service representative about what the issue type might be, what potential actions they could be taking, and which potential response templates they might want to work off from in order to formulate the final response. Now, obviously, the final call always lies with our CSRs, but the AI has shown to greatly improve the response speed of our customer support representatives whilst keeping the quality high. And similar to the forecasting platform, we have many transferable components in the natural language and conversational AI space, again, making it very ripe for platformization. Here I'm showing a high-level diagram of the common components that we have identified across conversational AI and natural language, and that we have been implementing towards. As mentioned in the early stages, the first step is really to translate text and speech to an intent, so the topic of conversation. And this is done by the semantic parser or natural language understanding unit. Now, many examples involve a back and forth conversation, and so we also want to maintain the state of the system. And this is what the dialogue manager is for. Now, finally, the semantic representation needs to be translated back into human understandable form, and this is done by the language generator. For the third and final platformization of a specific data science area, I want to talk about a very recent development that I'm personally extremely excited about. It is semi-automating data insights generation. I'm sure that many of you get questions similar to the ones shown on the left-hand side, and so do we. Every week, people are spending hundreds of hours at Uber generating insights. And this is a highly manual process still. So we have been thinking about, can we not just auto-generate suggestions to such answers by scanning through the data? And then we wanted to take it a step further. Why even wait until somebody asks a question and puts forward a hypothesis? This will always be limited by the number of people and the human hours that we can have in this space. Why not have an algorithm scan through our data and present interesting insights that now can be combined with the business acumen of our business partners as well as analysts, for example. So really machine-assisted decision making. We have built an early proof of concept and released it in alpha phase internally, and I've gotten really massively positive responses on this front. We've gotten feedback that the algorithm was able to make suggestions that humans hadn't even thought about. And so I think if we can be successful with this endeavor, this will completely revolutionize how we do data analytics and insights generation at Uber, and I think also across the industry. In the final section, I want to give a brief overview of the strategy of commoditization of data science. Now, obviously, building platforms can take quarters, perhaps even years. So how can we set up our specialist data scientists and platform builders up for success? We have here a three-phased approach. In the first phase, we embed specialists with our business partners. This allows them to understand the domain area very well, the pain points and the opportunities, and they can bring back informed decisions on how to build platforms. It also allows us to tackle use cases right there and then, having immediate impact on the user experience and gaining trust with our partners. That's, of course, not very scalable. So in a second approach, we build recipes or workflows. This might be an IPython notebook or a talk that gets recorded, so that other data scientists who might not be domain experts can start working off of these recommendations. And then finally, we wisely choose our use cases strategically to enhance the platform with every single use case we take on and reuse more and more of the platform along the way in order to build these push-of-a-button, completely automated platforms that can enhance decision-making for internal stakeholders. In case you're interested in learning more about this area, we actively publish on our engineering blog post. And with this, I would like to thank you very much for your attention.